Hello, Dr. Schreifels here. I thought I would go over for you how to figure out the radius of one of the elements that are involved in an ionic compound with a cell structure of body-centered cubic or BCC. So that kind of a cell structure is shown in this little figure on the right-hand side. So you have anions at the corner of this and you can tell they're anions because anions are usually larger than the cations. So the red ones are the anion part, and the cation is inside the crystal structure, touching through the diagonals here. So from this atom through the green to the red atom in the back, those are where the cation is touching the anion. So in this problem, you're given that it's body-centered cubic, a compound AB. You're given the density, so that's how many grams there are in a cubic centimeter of this. Now, the interesting, neat thing is that this density holds true for small amounts of this, but it also holds true for much larger amounts of this, like 5 grams per cubic centimeter. A cubic centimeter is a huge compared with an individual cell. So we're also given in the problem the ionic radius of A. And we have to figure out, so that's the cation in the center, and we have to figure out from that the ionic radius of B minus. We're given the atomic mass, or the atomic mass of in grams per mole of each of the two elements involved in the bonding. So how are we going to get from these pieces of information to the length of the radius of one atom? So we recognize that this unit cell here has 2 atoms in it. It has a net 1 atom for the red balls and net of 1 atom for the green ball. So that also gives the formula in 1-to-1. If we can figure out the mass of 1 atom of A and 1 atom of B, that will be equal to the mass of the cell. Now, if we know the mass of the cell and the density, density is mass over volume. If we know the density and we know the mass, then of course we can fairly straightforwardly figure out the volume. And granted that this is a cubic structure, the cube root of that will give the length of the side. We usually call that L in this kind of a problem. Now, for us to get to the final answer, we have to figure out what the diagonal through the face is. So that's this diagonal here. And that will help us to figure out the diagonal through the center of the cube, which is what we're really after. Because once we know the diagonal through the center of the cube, we know that that length is 2 times the radius of A plus 2 times the radius of B. It's the diameter, the sum of the diameters of the 2 atoms, basically. So that leads us to the radius of B, and that would be what we're after. All right, let's work first on the mass of the unit cell. Simple way of doing that is to figure out the molecular weight of the compound, divide it by Avogadro's number, and that gives us the mass of 1 atom of each, which is what we're after in the problem. So that's this number here. Now, recognizing that the volume of the cell is the mass divided by the density, that's just a rearrangement of our normal density equation. We should be able to figure out the volume of the cell by taking the mass that we calculated and dividing it by 5.29 grams per cubic centimeter, or get 6.42 times 10 to the minus 23 cubic centimeters. Well, of course, we can get the length of the side from that, just using basic geometry. We know that the volume is the length for this kind of a structure is the length of the side cubed, or if you want to solve for length, you just cube root that, and you get that the length of the side is the cube root of the volume. So that's what's done here. We took our volume that we calculated up here, put it in here, and take the cube root of it to get this. So we're going to convert that to picometers. I presume you all know how to do that. Now, the next thing is we're going to define two terms that are similar but not exactly the same. We're going to get the diagonal through the center of the cube. We're going to call that D. And this diagonal across the face, that's this diagonal from here to here, is going to be called X. So X is going to be the length of this side squared plus the length of that side squared will give us this squared. So X squared equals L squared plus L squared, or if you want to express it in terms of X, X is equal to the square root of 2 times L. Now the diagonal through the center of the cube is this squared plus, in other words, the length of the diagonal of the face squared plus the diagonal of this squared. That gives us Pythagorean theorem, lets us figure out this length here, which is D. So the net result is that D squared equals X squared plus L squared, but we already said that from here, or here, depending on what you want to use, we said that X squared is equal to 2L squared. That gives us, the total would be that this would be D squared equals 3L squared. Take the square root of both sides to get this, and multiply by L. We said up here was 407. So that gives us 705 picometers for the diagonal through the face, through the center of the cube, like this. Now we go back up to what we said up here, that this diagonal, which is 705 as we calculated, is equal to 2 times the radius of A plus 2 times the radius of B. You can do very simple math, divide both sides by 2. In other words, to get on the one side, you get 352.5. Now we can put in the radius of A was 160, and then you can bring that over to the left side with the 352 to get that the radius of B must be the difference between these two, which is 192.5, and you're done. Picometers, of course. And that's the end of your problem. I would point out, just as a last thing, that there are other versions of this kind of a problem that you might encounter that are essentially the same problem, where you're just asked to calculate something slightly different. So, for example, one thing you might be given is the radius of A and B, and its molecular weight, and the kind of crystal. Let's say it's the same crystal structure. And using what we have up here, you can figure out the mass of the unit cell, just like we did here, just like we did in this first part. And knowing the length of the side, you can figure out the volume, and the length of the side you can get from this diagonal through here, using the relationships here that we talked about. That ultimately leads you to the volume of the unit cell. And if you know the volume of the unit cell and the mass of the unit cell, you get the density. Okay, so that's hopefully is something that you find useful. Hope you have a good rest of the day.